Welcome to Lab 2. In this lab, we are going to build a 4-bit ripple carry adder. So let's begin. In the last lab, we had a brief introduction to VHDL. We saw how to describe a logic circuit as a combination of entity along with its interfaces called ports and its architecture. We also saw some structural descriptions, how to define an entity and then use it as a component to build more complicated circuits and how to connect them using signals. We saw the importance of writing a test bench, and we saw some features that VHDL provides in writing a test bench. These features are statements that are not synthesizable but which are useful for writing these test benches, for example time delays and so on. And finally, we saw a concrete example of simulation using the EDA playground platform. So this was the lab 1 exercise. You were asked to build a half adder using these XOR and AND gates as components. Let me briefly go over the solution for this lab, because in the beginning some solutions will be provided for you to verify whether what you did was correct. So here's a simple solution. It's very straightforward. First we write the entity and architecture for a simple AND gate. Similarly, we write the entity and architecture for a XOR gate. Notice that the same names A, B and C were used for both because it doesn't matter. When we are talking about A, here we are limited to this scope. So there is only one A in the scope, so that's fine. Similarly, when we are using A, this A corresponds to the scope, right? So it's okay to use the same names in different scopes. It's alright, there's no confusion here. Now we write a description for a half adder that uses this AND gate and XOR gate as components. So first we describe the ports. Notice that I'm again using the same names A, B, sum and carry. You can use different port names, but it is okay to use the same names here if you choose to do so. Because when we are going to talk about A, B, S and C within this architecture, it will refer to these ports. So let's see how to write the structural description. This is the architecture. Before the begin block is the declaration. So we are going to declare some things. We are going to declare two components, component AND gate and component XOR gate. And then we will create an instance of the AND gate and an instance of the XOR gate. And we are going to just map the ports directly to our ports of the half adder. So in the port map statement, this is directly declared in the order in which the ports actually occur in the component. So they occur in the order A, B and C. So what this means is port A of the AND gate is connected to this A here, which is port A. Port B of the AND gate is connected to port B of the half adder, and port C of the AND gate is connected to port C of the half adder. Similarly for the XOR gate. So this is a direct way or a direct syntax for the port map statement, where you just list what is connected to the ports in the exact same order in which they appear here. Another way is to explicitly list out what is connected to what in this manner. This is another syntax in which I say port A of the component half adder is connected to this signal and this port is connected to this signal and so on. So this is an alternate way of describing port map. So let's look at a test bench. I hope this is clear. The test bench is similar to what was used in the example in the last lab. We have a test bench that has no ports. In the architecture of the test bench, we first declare the half adder component that we want to use, and we have some extra signals, input signals and two output signals. What we will do is we will assign some values to the input signals and examine the values on the output signals. So we instantiate the half adder component here. Half adder, we map the ports. Port A of the half adder is connected to the signal A in, port B is connected to the signal, and so on. And then we assign some values on A in and B in. Okay. So this is exactly similar to the other examples we have seen so far. Okay. So now let's move on to today's lab. In lab 2, we are going to study some features of VHDL. In particular, we are going to study port modes. Ports can be input, output, or in-out ports. We are going to study some common types of ports or signals. We saw this example, we saw bit, but we have to see what is bit vector, standard logic vector, and so on. We are going to do a quick recap over structural descriptions versus behavioral descriptions and concurrent statements in VHDL. Okay? And as an exercise for lab 2, we are going to build a 4-bit adder circuit. So let's move on. So consider this entity, right? It can have ports which are input ports or output ports or ports of type in-out. An in port can be read, but it cannot be updated. So for example, in the architecture for this module, you cannot have a statement that puts some value, assigns some value on the input port. This is not allowed. Input ports can only be read. Similarly, an output port can only be written to from within this entity. You are not allowed to read the value of the output port. So this entity can write to its output port, but this can be connected to another entity or a signal which can be read. So finally, something else can read from this port, but this entity can only write to the output port. Alright. Finally, there is such a thing as called an in-out port. Okay. In this type of a port, the entity itself can assign a value as well as read the value and use it. So the entity can assign a value as well as read the value that is there on the port. Such ports are useful for modeling circuits where there is a common shared wire or a shared bus, and several things may be reading or writing to it in a well-defined manner. Okay, at a time only one thing may be writing a value on this wire. We will see this example later on, but right now we will restrict our usage to only the in and out ports. Okay, the in-out port serves some special purpose, which we will see in examples in later lab sessions. There are some other types of ports, for example buffer and linkage, which are rarely used. We will not see them in this lab, we will not pay attention to them. So let's see the syntax. Okay, so here is the entity port, then we say the name of the port, the mode of the port, whether it's in or out, and this is the type. This is the syntax. This is the mode and the type. In this example, all the ports A, B, C and D are of type bit. They are a single bit. So now let's see what other types of ports can exist. So what we are going to see is data types. What are the different types? This same thing applies to ports or signals or to other kinds of objects in VHDL. A bit type of port or signal can only take the values 0 or 1. Okay. Now many times we may want to model some circuit that has a bunch of input bits. For example, we want to model something that adds two 8-bit numbers, okay, and produces an 8-bit result and a carry. We want to build such a circuit. So these are actually 8 bits and they look like actually 8 parallel wires, right? Now it would be tedious to actually have 8 port declarations. Like for example, if this whole bunch is called A, we may call this A7, A6 all the way to A0. It may be tedious to have such a individual declaration of each port. So VHDL allows you to describe a vector of signals. Okay, it's akin to having an array definition in C. So this is called a bit vector. A bit vector of is a vector of type bit. Visualize it like a bunch of signals, each of type bit, and they can all have a same name, a single name, and individual bits in this vector can be indexed in this manner. So unlike in C, we don't use square brackets, we use a round bracket. So A3 refers to this third value. So A3, sorry, 3210 for example. So A3 can, so the third bit in this bit vector can be indexed using this round brackets. Okay, this is very useful when you want to describe inputs which are actually in a bunch. Let's say 4-bit input, 4-bit out, and 4-bit output. Okay, now let's move on to a new type called standard logic. Okay, so standard logic is essentially something to describe a single wire or a signal, right? So it's exactly like a bit, but it is more close to the reality. In the real world, this is a wire. Let's say if you are representing logic signals using voltages, the voltage may not be exactly high or low. It could take some intermediate values, or this wire could be not connected to anything. It could be open circuit, right? Such things could actually happen in the real circuit. This is open circuit, for example. Or there are the two things simultaneously driving a high and a low value on it. So what should be the actual value on this wire? Such things could happen in real circuits. So just restricting ourselves to 0 or 1 may not model circuits in a realistic manner. So we have a type called standard logic, which allows some other values besides 0 and 1 to be assigned to a signal. Okay, so for example, there is a value called u, which means undefined or uninitialized. So for example, you design a circuit, okay, and there's a signal, and which is later used as an input to something else, but this is itself not initialized and not connected to anything. So what should be the value here? Well, it will appear as u in the simulation, and then the designer will come to know if there is some u values appearing, that oh, I forgot to initialize. So these things are useful. Okay, Z means high impedance, open circuit. So these are useful for detecting errors in modeling, as well as for modeling some other things where multiple things are driving a value onto a signal and so on. So similar to a bit and a bit vector, a single signal can be used can use the type standard logic, and a bunch of these signals can be described using standard logic vector. So it's a vector of signals or ports, each of type standard logic. Okay, so now since standard logic is more useful in catching modeling errors, henceforth in this course we will not be using the type bits, but we will stick to this types standard logic and standard logic vector for all our signals and ports. Okay, so we will be using these two types. So let's see an example of how to use them. So here is a circuit, it's called MUX4. It has a lot of inputs. Okay, it has 4 bunches of inputs: A data, B data, C data and D data. Each is of type 8, each has 8 bits. Okay, then there are 2 single bits, select 0 and select 1, and an 8-bit output called data out. The behavior of the MUX, actually also called a multiplexer, is as follows. Depending on the select lines, this data out becomes connected to one of the inputs. For example, if select is, these are 0 0, then whatever values are on A data appear on the data out. So if select is 0 0, then this is effectively connected to data out. All 8 bits of A data are connected to data out. Whereas if select is 0 1, sorry, let's call this select 1 select 0. If this is 0 0, then A data is connected. If this is 0 1, then B data is connected, and so on. So this is called a multiplexer. Okay, depending on the values of the select ports, any one of these things could be connected to the output. There are 4 of them, so you need 4 possible combinations of the select lines. That's why you have 2 bits. Okay, so there is 0 0 0 1 1 0 and 1 1. Depending on each of these, one of these inputs will be connected to the output. Now if you were to declare each of these ports as a single bit, that would be very tedious, so we are going to use standard logic vector. Let's see the syntax. Entity mux4 is port. A data is an input port of type standard logic vector 0 to 7. That means the index ranges from 0 to 7. Okay, and if I were to assign a value that looked like this, 0 0 1 0 1 1 1, this would mean that since I'm saying 0 to 7, it would mean that A data 0 would be assigned the value 0 and so on, and A data 7 would take the value 1, because I'm saying 0 to 7. Okay, so 0 corresponds to the leftmost thing and 7 is the index of the rightmost thing. It's a bit unnatural to read it this way, because when we are typing, when we usually design circuits, we usually mean we write it this way. For example, 1 0 1 1, if A is this, we would index this as A0 and this as A3, most significant bit. This is more natural. So this is also allowed. If you declare something as standard logic vector 7 down to 0, then it means that the leftmost thing has the index 7 and the rightmost thing has the index 0. Okay, so let's see an example. Okay, let's say I assign a value, data out is assigned the value 1 0 1 1 1 1 1 1, for example. Then because I have declared it as 7 down to 0, this leftmost value is A7, sorry, data out 7, data out 7, this is the index 0, this is the index 1, and so on. Okay, 7 down to 0, the leftmost is 7, the rightmost is 0. So this is more natural and more commonly followed also. So I would recommend all of you to use the down to notation where required. Unless you really require to use this, it's allowed in some cases. Right? Should be okay to use this where it's more natural, but I would encourage you to stick to one notation, not to mix up the notations like in this example, which this can be confusing. So we will just stick to the down to from here on. So this is the syntax. Okay, you specify the port name, you specify its mode, and you specify its type. So look at this port, it is not a vector, it's a single input. So select 1 and select 0 are single inputs. Instead of writing it this way, we might have written a select in standard logic vector 1 down to 0. We could have given this bunch a single name. Alright. So let's come back to the standard logic. What is this standard logic? So remember, if it is a type bit, it can only take the value 0 or the value 1. But standard logic data types, the objects of this data type, can take some other values also. It can take one of these values. If you notice, 0 and 1 is there as usual. U means uninitialized. Okay. Z refers to high impedance. That means it's open circuit. There's nothing connected to the signal. Okay. Then there are these other values which we will not focus on right now. We will see them in later examples. Okay. But you are encouraged to read up on what they mean. So X means forcing unknown. W and L and H are weak unknown, weak low, weak high. Okay. And dash also means unspecified. That means it could be anything. Do not care. We'll see how to use them later on. So right now we will stick to this standard logic. If you don't initialize it, it will appear as U, or it will appear as 0 or 1. We will see these most commonly occurring in our examples. Okay. So here is another example. This is our test bench. So we declare two signals. So just like in ports, this can be used for signals. Signal S1 and S2 are type standard logic vector 3 down to 0, and they are initialized to this value. So when you want to assign a bit, you use a single quote. For example, signal A is assigned this value, a bit or a standard logic vector. But if you want to assign to a vector, you will use double quotes. Okay. Double quotes are used to assign something to a vector. So S3 is standard logic vector 0 to 3 and this. So that means this is assigned to A3, what is that? S1. S1 3, this is assigned to S1 0 and so on. Whereas if you use the 2 notation, this is actually S3 0 and this is S3 3. Okay. So the way you are specifying the index, whether it goes from the leftmost to the highest index and so on, depends on whether you are using down to or to, and we are going to stick to the down to format. So let's come back and do a quick recap of what is meant by a structural and behavioral description. Okay. So first of all, it is somewhat of a subjective word. Is not very concrete or very objective, what somebody could call structural and what somebody could call a behavioral description. But let's see what it is commonly meant to be. So if you describe the architecture of some entity as an interconnection of components, okay, if you describe its architecture as an interconnection of components, this is what is meant by a structural description. You describe its structure. You describe how it is structured, what are its components, how are they interconnected, and so on. Okay. If you describe the behavior, if you describe the architecture of this entity in a behavioral way, not as an interconnection of component, but just specifying, for example, C is assigned A XOR B. We are describing that C should be an XOR of A and B. We are not saying connect an XOR gate per se, but we are just describing it in a more direct manner. We are just saying how this entity should behave. This is called a behavioral description. Actually, in particular, behavioral description refers to things that are described using the process block. We have not yet seen what is a process block. We will see an example of this in subsequent lectures. But right now, think of it as this behavioral description is when you describe the architecture in terms of how the entity should behave. What is the relationship between the output ports and the input ports? Okay, how it should behave in a more abstract way. Okay. This does not imply a particular way the circuit is actually built. So when you say A XOR B, we don't know whether the circuit would actually get built using an XOR gate or using a combination of AND gates and OR gates or using NAND gates. It could be built in any particular way, but we are just describing what it should do. C should be an XOR of A and B. Whereas this kind of description, we are saying that the entity should in turn have these three components. They should be connected using signals in this particular way. So we are concretely describing its structure. Whereas in this example, we are just describing what the output should be, what should be its behavior. Now obviously, you don't have to choose one or the other. The architecture could be a mixture of statements which are structural and behavioral. Okay. For example, we can say the entity has these components, okay, whereas this signal is actually an AND of some other signals, and so on. So the actual description could use a mixture of the two also. So here's a picture explaining this. So for example, if we were going to make an adder, let's say A and B are all standard logic vectors of some width, we could write a higher level description, a behavioral description, saying S should be assigned A plus B. So how is this addition to be implemented as logic circuits? You could describe it in a more detailed manner as in some sort of a detailed manner as an interconnection of basic AND or XOR NOT components. This would be a structural description. Okay, and either of these could be converted actually into a physical circuit implementation. So this would be more directly implemented as a circuit, but this has to be converted into a circuit using a synthesis tool. Synthesis tool will automatically be able to convert some kinds of these descriptions into a circuit. They would be able to infer this and convert them into a logic circuit. So this actually reduces the designer's work. These are doing the designer's work using some standard algorithms. Okay. Now we will come back to a recap of concurrent statements in VHDL. This is just a recap because it's very important. Remember, in the last lab we described that VHDL is not a programming language. You're not supposed to think of a description of VHDL like a programming language. Okay? So this is describing hardware, it's describing concurrent things. So let's come to this example. There is an architecture, and in this architecture these signals A out, B out, C out and E out are assigned some values. Okay, this is A out is A1 and A2 and so on. If you notice, each of these statements, they are written one after the other, but it does not mean that they happen one after the other. They are all concurrent. They describe things which are going on simultaneously. Okay, so we have statement 1 semicolon, statement 2 semicolon and so on. These statements are concurrent. They are describing things which are going on simultaneously. So this signal is being assigned an AND of A1 and A2, while at the same time B out is being assigned B1 or B2 and so on. This is very important, and that's why I am repeating this again. Statements in VHDL are concurrent. There is an exception though. There are some kinds of statements which are sequential. We will see what that is. So VHDL has something called a process block. This is how it looks like. We give it some name. Is a process. Some process is a process. These are its input triggers. Then there is a begin and end process. This whole thing is called a process block. And within it there can be some other statements. Some statements, semicolon and so on. Now within a process block, the statements that occur are sequential. They are executed one after the other. Okay. But the whole process block itself can be called as one statement. This itself is a statement, right? This is statement 1, this is statement 2, statement 3, statement 4, because there is a statement, semicolon, statement, semicolon and so on. So statement 1, statement 2, 3 and 4 with respect to each other are concurrent. They are all happening at the same time. Okay. Statement 1, statement 2, statement 3 and statement 4 are all concurrent with respect to each other. But within statement 1, there could be some things which are done sequentially. So right now it may not be clear as to what a sequential thing means in hardware, right? If these are happening concurrently, they refer to circuit elements which are existing at the same time. But within this statement 1, it may not be clear what it means when things are executing simultaneously, sequentially, for example. So this may not be clear at this point. We will see what it means in subsequent lectures. But just this was just described to tell you that as an exception, this process block is an exception. Okay, the things that occur within a process block are sequential, but other than this, all the statements are concurrent. So we will see concrete examples of a process block later on when we study sequential circuits. Okay, so right now just remember that there is such a thing called a process block in which the statements that occur can be interpreted sequentially, but other than that, all statements in VHDL are concurrent. They describe things that are happening simultaneously. Now let's come to Lab 2 exercise. Okay. The goal of this exercise is to build a logic circuit that can add 4-bit unsigned integers. So for example, 1011 and 0010, we should be able to add and produce a result. If you do this manually, how do we do this? We add this one position at a time, starting from the least significant bits. So 1 plus 0 is 1, 1 plus 1 is 2, that is 1 0. So 0 is here, and this 1 is a carry in this position. So 1 plus 0 is 1, 1 0 is 1. So this is the result. Let's take another example, 1011 plus 0 1 1 0. Okay, so this is 1, 1 plus 1 is 2, so there is 0 and there is a carry out. So we have to add these 3 bits, 1 0 and 1, that's again 2, so this is a carry out of 1, and 1 plus 1 is 2, so 0, and there is a final carry out. So notice that when you add these 4-bit numbers, the result can be 4-bit plus 1 carry. So the total result is of 5 bits, right? Result can be of 5 bits. Also notice that if we are adding them in these groups, we need a capacity to add 3 bits. So let's call this A, let's call this B. So there is a bit of A, a bit of B, and a carry in that position. So at each bit position, we need a capacity to add 3 bits. So in the last lab, we designed a half adder which can add 2 bits A and B, but that's not good enough. To make a complete adder, we need to be able to add 3 bits, A, B and a carry in. That's called a full adder. Okay, full adder is just a circuit that can add 3 bits to produce a 2-bit result, because the maximum sum of 3 bits is 1 plus 1 plus 1, that is 1 1. So you need 2 bits. The 2 bits are sufficient. So we will design a full adder, and we use 4 such full adders to make a circuit that can add 4 bits. Okay, such an architecture is called a ripple adder. That means the carries are rippled through the circuit. You add these 3 bits, you write the sum, and the carry goes as an input to the next 3. You add the sum, you produce a sum, the carry of that goes as an input to the next, and so on. So the carry is rippled through these bit positions. That's why it's called a ripple adder. So let's first design a full adder. It's a circuit that adds 3 bits, A, B and C, C in, carry in. So these are all the possible combinations of A, B and carry in. And this is the sum and the carry out. So if you notice, it's just a sum of all these 3. For example, this is 1, this is also 1. Then there are 2 1s, so the sum is 2, that is 1 0. So carry is 1, sum is 0. And finally, when all of them are 1 1 1, the sum is also 1 and the carry is also 1. This is binary representation of 3, right? So we can use these truth tables to infer a circuit for the full adder. So think about it. What would be the expression for sum in terms of, what would be the expression for sum in terms of A, B and carry in? What would be the logical expression for sum, and what would be the logical expression for C out in terms of A, B and carry in? So sum is 1 only when exactly one of them is 1, or when all of them are 1. So when an odd number of inputs is 1, then the sum is 1. When there is an even number of inputs, which is 1, then the sum is 0. So what should be the logical expression? Similarly, figure out a logical expression for C out. Right? Now you can derive the logical expression using these truth table values and simplify them. Okay. So this is a part of the exercise to figure out this logical expression. Now you can write a VHDL description for this full adder, right? So for example, if you found out that sum was A XOR B XOR C in, so verify whether this is indeed correct. And what is C out similarly? So you have to build first such a full adder circuit, and then use this full adder as a component in a ripple carry adder. So this is the architecture of a 4-bit ripple carry adder. So first you, for example, 1011 plus 1010, want to add these. So first you add the leftmost bits, right? So you add the bits A0, B0 at the index, you produce sum 0, and you produce a carry 0, which becomes an input carry to these 3 bits, and so on. So since we are using full adders that can actually add 3 things, why not have a carry in into the circuit? This will be useful if you want to add an additional bit. Okay, there is a carry in also, and finally there is a carry out. So this is the architecture. There are these 4 full adders. Okay, to each adder you connect these inputs. So finally this ripple adder has inputs A of type standard logic vector 3 down to 0 of size 4. Again B, standard logic vector of size 4, that is 3 down to 0. It has a carry in, a single bit. It will produce a 4-bit sum and a single bit carry out. So this would be the block diagram of the ripple adder, and internally these bits will be split up as A3 up to A0 and connected to these adders. So this is the architecture, and the carry in of the first stage becomes, a carry out of the first stage becomes the input carry to the next stage, and so on. So take a moment and convince yourself whether this circuit will actually be useful for adding 2 4-bit numbers, A and B. A is a 4-bit number, B is a 4-bit number. See if this architecture will be indeed adding the 2 inputs. So you are required to design the full adder, use it as a component to create another entity called ripple adder, use that in turn as a component inside a test bench, and write an appropriate test bench. Okay. So this is the exercise. You are required to write a architecture for a full adder. Then write the architecture for a 4-bit ripple adder using these as components, and write an appropriate test bench. These are the submission instructions. Okay. Now, as a reading assignment, think about what you would do if you were required to generalize this description to create an n-bit adder. Not just a 4-bit adder, but an n-bit adder. N could be a parameter. How would you do this? So this can be done using generics. Okay. what we do is we write the description in terms of n. So for example, if you were to write an n-bit port, we would say n down to 0, where n can be some positive integer. And we describe the entity like this using n. Instead of using 3 down to 0, we just describe it using n. And when we actually create a component of that entity, we specify what is n. We say n is equal to 3. No, sorry, n is equal to 4 in this case, right? N is equal to 4. So this will be n minus 1 down to 0. Okay. So if we want to make a 4-bit adder, we will pass n is equal to 4, but in the actual description we will say some standard logic vector n minus 1 down to 0. That means if n is 4, this will be 3 down to 0. So we describe the architecture in a generic way using a name n instead of actual number. This can be done using generics. There is a very specific syntax for doing this. It's called generics. So you are requested to read up on this. Okay. And think about how you would write this description for a n-bit ripple carry adder. So that's it for this lab.